plugging a car into a charger that pours 1.2 megawatts. That's more power than a small office building, and your battery accepts it safely. Sounds like science fiction, right? Today we'll break down why that idea smacks into real chemistry and real heat, and whether next generation batteries can actually make it happen. So why this matters? You have probably seen headlines about 5-minute EV charging or solid-state batteries that fix everything. Faster charging is the holy grail for EV adoption, but pushing huge power into a battery is like stuffing a wild horse into a race car. The chemistry fights back and the heat shows up with a vengeance. In this video, I'll explain in plain English why current lithium cells struggle with sustained ultra-high C rates, what the thermal nightmare looks like when you try a 1.2 megawatt charge, and how pack architecture, cell-to-pack versus pack-to-chassis, and even cell-to-chassis changes the thermal playbook. The chemistry story. Why lithium-ion fights fast charging? Think of a battery like a set of tiny rooms where lithium ions run from one room to another. At normal speeds, everything is calm. At very high speeds, ultra-high C rates, those ions start tripping over each other, doors slam, and the floor gets sticky. Here's what actually goes wrong. The solid electrolyte interface, or SEI layer, on the anode is a double-edged sword. It forms naturally and protects the anode, but rapid charging stresses it. SEI grows unevenly or breaks and reforms, which eats up active lithium and raises internal resistance. Over time, that shrinks capacity and hurts life. When the battery is forced to accept current faster than the lithium ion can safely insert into the graphite or anode, lithium metals can plate onto the anode surface instead of intercalating. That's lithium plating. It's dangerous because plated lithium can form whiskers or dendrites that pierces separators and cause internal shorts. That's one reason batteries age quickly under aggressive charging. Fast charging also increases electrochemical overpotential. In plain words, the cell needs extra voltage to drive ions fast enough, and that extra voltage gets turned into heat. Heat speeds up unwanted chemical reactions and accelerates SEI growth. A vicious cycle. All of these effects are tied to three simple numbers engineers hate to see: current temperature and local state of charge. Push any of those too far and the cell pays the price. Is the solid-state batteries the promised land here? Solid-state batteries replace the liquid electrolyte with a solid conductor. That sounds small, but it changes the rules. Solid electrolytes can reduce flammable liquid exposure, open the door to lithium metal anodes, and in some design improve charge acceptance and thermal stability. In real tests and industry announcements, several startups and OEMs claim significant improvements in charge speed, energy density, and safety. And some auto groups are already partnering to industrialize these cells. But here's the catch: solid electrolytes are not a magic. They often suffer from mismatch at interfaces. The solid-solid contact between electrolyte and electrode can be poor, creating high local resistance and hotspots. Mechanical cracking during volume changes, which can create voids and resistance. And manufacturing scale, cost, and durability hurdles that are still being solved in the labs and pilot plants. Recent reviews show huge progress, but also points out the remaining materials and manufacturing bottlenecks. So yes, solid state can help with high rate charging, but timeline to mass production and real long-term cycle performance under megawatt charging still needs proof. Now, time for a thought experiment and a few plain math steps so the size of the problem lands. 1.2 megawatt is 1,200,000 watts. That's the rate electricity is flowing into the pack. To make it meaningful, the engineers use system voltage to convert to current. Many modern high-power systems target 800 volts for ultra-fast charging. So 1.2 megawatts divided by 800 volts gives you 1500 amps. A number that would fry most household wiring instantly. Now, real packs are not ideal. Some of the input power becomes heat. Even if the pack were 99% efficient, 1% of 1.2 megawatt is 12,000 watts. That's 12 kilowatts of heat to dump. If the pack is 95% efficient, 5% wasted is 60 kilowatts, which is the size of a small industrial heater. To show that as a calculation, 1.2 megawatt times 5% is 60,000 watts. And that heat shows up not as one nice warm surface, but as small hot spots inside cells where resistance is higher. Those are the places that fail first. A simple ohmic example helps explain how localized resistance matter. At 1500 amps, a tiny resistance of 0.25 milliohm in a path gives 1500 squared is 2,250,000 times the 0.25 milliohms gives you around 562.5 watts. So a single tiny spot with a quarter milliohm extra resistance can burn out over 500 watts locally, concentrated in a few square millimeters. That's how you get hot spots and thermal runaway initiation. Those small numbers add up fast when millions of amps squared comes into the play. Why cooling today's systems struggles? Most EV packs use liquid cooling plates, conductive paths, and sophisticated battery management systems. They work great for everyday driving and current fast chargers, like 150 to 350 kilowatts, but megawatt level charging stretches them. Liquid cooling has finite heat transfer across metal plates into coolant and then into radiator. You need massive coolant flow and big radiators for 10 of kilowatts of continuous waste heat. Air cooling can't handle it except in small bursts. Immersion cooling, or meaning submerging cells in dielectric fluid, is very effective at moving heat but introduces packaging, maintenance, and safety complexities at scale. Phase change materials absorb heat during brief spikes but need time to recover and won't help sustain megawatt loads. Recent reviews summarize trade-offs and show that the extreme charging, you don't just need better cooling, you need a different system architecture. Design choices that change the thermal equations are here. This is where architecture, how you arrange cells and cooling, matters as much as cell chemistry. Cell-to-pack skips modules and places cells directly into a pack housing with integrated cooling plates. That reduces empty space and trims weight, but it also concentrates cells tightly together. The benefit: there are more energy per volume and potentially shorter thermal paths to cooling plates. The downside: less modularity and potentially faster propagation paths for heat if something goes wrong. For pack to chassis or cell to chassis, it takes the idea further. The battery structure becomes part of the vehicle's chassis. That spreads mechanical loads and can open new thermal channels. The chassis itself can be used as a heat sink or routing for coolant lines. It also can improve volumetric efficiency. But integrating cells into chassis raises repairability, crash safety, and manufacturing complexity questions. And it requires the cooling strategy to be part of the whole car design, not just the pack. Here's a cheat sheet comparison. Regarding cell to pack, it is more compact, lighter, better energy density at pack level. It has cooling plates. The cooling plates can be close to many cells. It is harder to isolate failures, and thermal propagations can be quicker. Regarding pack to chassis or cell to chassis, it uses vehicle structure for rigidity and possibly heat spreading. It can reduce redundant structure and weight. It requires tight co-design for cooling, crash, and manufacturing systems. All of these choices change where heat is created and how fast it can be whisked out. The problem amplified here. What happens during a 1.2 megawatt attempt? Let's imagine an aggressive scenario and walk it through visually. You try to give a battery 1.2 megawatt for several minutes. Even with modern cells, small imperfections, tiny SEI variations, or slightly misaligned cooling contact points create local resistances. Those spots get hotter faster than the BMS can act. As temperature rises, internal resistance rises, producing more heat for the same current. SEI accelerates its destructive chemistry. Lithium plating risk increases if parts of the pack are at low state of charge or cold. If a hot spot reaches a critical threshold, thermal runaway can start and then propagate. Thermal runaway is a chain reaction. Once one cell goes it can cook the thermal runaway is a chain reaction here. Once one cell goes, it can cook its neighbors. The hotter it gets, the faster the reaction runs. Preventing that chain at megawatt power is the entire engineering challenge here. Real standards and works on the megawatt charging aim to move beyond 350 kilowatt to multi-hundred kilowatts and megawatt levels for heavy vehicles. But industry sources and reviews consistently say that cooling and safety systems becomes the limiting factor, not just how much power the charger can deliver. So how engineers are trying to fight the heat? This is the part where engineering gets creative and little ruthless. Active liquid cooling with custom plates and high flow rates. Use scale pumps and heat exchangers, but that adds weight, parasitic power draw, and complexity. Immersion cooling. Cells are submerged in a dielectric fluid that carries heat away extremely well. It reduces temperature gradient and local hotspot, but changes serviceability and cell design. There's distributed sensing and ultra-fast BMS. More sensors, faster algorithms detect anomalies milliseconds sooner and throttle or reroute power. This relies on near-perfect models and redundancy. They do cell design tweaks, low internal resistance chemistries, thick plate tabs, improved current collectors, and reduced contact resistances. These all cut IR squared losses. Pack zoning split the pack into isolated thermal zones that can be disconnected or cooled independently to stop propagation are one of the approaches here. There are some hybrid approaches as well, combination of what we described before. The common theme is that you need multiple layers of protection because no single fix is enough at megawatt levels. Reviews of thermal management systems lay out these trade-offs in detail. Here's the optimistic beat if you can combine. Cells that tolerate higher currents without plating or SCI collapse, and packed layouts that make heat paths short and accessible to heavy cooling. Then you get a system that can handle more power safely. These recent industry announcements and trials, startups, and partnerships show prototype solid state packs going through automotive validations and demonstrator fleets. They promise faster charge, better safety, and higher energy density, all helpful for megawatt ambitions. But many of these claims are for early pilot or specific conditions. Scaling to mass production and real-world durability under repeated extreme charges is still being proven. Here's the core truth. Speed versus life and safety is a three-way trade-off. You can push charge speed, but you either accept faster degradation and shorter battery life, or pay heavy engineering and cost to cool and protect the pack, or change the chemistry and the pack architecture to reduce the problem at the source. The coolest tech in the world won't help if the heat has nowhere to go. At the same time, the best cooling in the world won't help if the chemistry plates lithium metal in a way that creates standards. Both chemistry and thermal architecture must advance right together. If you want a short list of what matters the most when people talk about ultra fast or even megawatt charging, here it is. Cell chemistry limits charge acceptance. SEI growth, lithium plating, and overpotential are the killers here. Heat is power's twin. Even small inefficiencies at megawatt power mean tens of kilowatts of heat you must remove fast. Do the math, like 1.2 megawatt times 5% is 60 kilowatt if you're only 95% efficient. That's huge. Architecture matters. Cell to pack and cell to chassis gives volume and thermal advantages, but moves complexity into vehicle design and safety systems. Solid state helps but isn't a silver bullet yet. Progress is real and promising, but manufacturing, interface resistance, and durability under repeated extreme loads are active challenges.